All right. All right, so we're going to go ahead and get started. Thank you, everybody, for showing up to the parallel computing and MATLAB workshop put on by RCC. I am Alex Townsend. I'm one of the application specialists working at the Research Computing Center. RCC is the Research Computing Center. We're a section of the Information Technology Services on campus, and we run the supercomputer on campus. And part of that involves us running these kinds of workshops to help teach some of the tools that we have available. So I'll stop for questions, but I'll stop for questions as I have time. If anybody in person has questions, just raise your hand, and I'll be happy to answer them. If anybody online has questions, just have one of the moderators. Please post them in the chat, and then one of the moderators. So in this workshop, we're going to go through a few different things. The first thing we're going to go through is a basic introduction to what parallel computing is, and we'll cover a couple of different important terms and concepts, particularly terms and concepts as they apply to MATLAB specifically. We'll talk a little bit about parallel computing setup within MATLAB, and how to go about getting started, getting a MATLAB job started on the Research Computing Center systems. And then we'll talk about a couple of different strategies for parallelization within MATLAB. We'll cover automatic parallelization, which is just functions that already have parallel computing enabled, and how to go about using that. And then we'll talk a little bit about parallel for loops. If we have time, there's a couple of other strategies that I might go into, but these are sort of going to be the main work. So to get started, let's talk a little bit about what parallel computing is in the first place. So parallel computing is effective. So when you're doing computing or programming in general, a program is effectively a sequence of instructions. Your computer will read them line by line. If it's an interpreter, if it's a compiler, it's the same thing effectively. But it will read your instructions line by line and execute them. What parallel computing tries to do what parallel computing does, it takes those instructions and breaks them up into independent sections, and then tries to run as many of them as it possibly can at the same time. Now, this comes with a couple of important caveats that we'll talk about, but effectively that's what it tries to do. It tries to take a big chunk of work that otherwise would be done one step at a time, break it up, and give it to a bunch of different workers that can all kind of work on different pieces of it at the same time. There's really two main paradigms in parallel computing. There's multi-core and there's distributed computing. Multi-core computing is what it's sometimes called it sometimes gets called shared memory computing, or if you've ever programmed in C, you might see OpenMP, or multi-thread computing. These are all effectively the same thing. Distributed computing is, and what multi-core computing is effectively you have a big computer that's chunked up into a bunch of different processors, and those processors all share one global memory space. So all your variables, all your data, all your information is stored in this big block of memory, and all your processors can access that big chunk of memory at the same time. So multi-core computing shares memory, and then all the individual processors work on pieces of that at any given time. Distributed computing is a little bit different in the sense that instead of having a big chunk of cores and a big chunk of memory, and all the cores access the same chunk of memory, it's essentially each individual core gets chunked off with its own separate bit of memory. So effectively, each core has a little bit of memory that goes with it, and then that has the advantage of making it so that the actual program you're working on doesn't really care where those processors and memory are. So you could have a processor with a chunk of memory over on that computer on the far side of the room, another one on the other side of the room, another one in Canada, and as long as those processors and their memory can communicate back and forth between each other, then the program can continue to run. Distributed computing is if you've ever used something like multiprocessing in Python, or if you've ever used something like MPI and C or Fortran, it's all based on the idea of message pass. So each individual processor only has access to its little chunk of memory. It doesn't have access to anybody else's chunk of memory. So if it wants access to something that's in that it knows another processor has access to, it has to send a message to that processor saying, "Hey, hey, I know you have access to some specific piece of data or variable. I need access to it. Can you send me a copy?" Then that processor will respond with a copy of it, and then it will work on that and send the message back with the updated value. So this is effectively kind of what I did, what I just said. This basic concepts are serial versus parallel. I should also talk a little bit about some key terminology that I'm more than likely going to use throughout the presentation. A core and a node. A core is an individual CPU core on a given computer. So if you ever hear your desktop or your laptop might have a big CPU chip that's chunked into like 4 or 6 cores. Each one of those CPU cores is effectively a little device that can run these step-by-step serial processes. A node is an individual computer. So it's effectively like your desktop or your laptop or a server blade sitting in a data center somewhere in Canada or out in the Sliger building here at RCC. So you can think of it as a core is an individual unit that runs instructions or runs code, and a node is a physical computer box like your laptop or your desktop. So as I just described, multi-core computing is using multiple CPUs at the same time. It usually occurs on a single node or a single computer. Distributed computing is where you have a bunch of computers, a bunch of nodes, each of which have a bunch of processors, and you can leverage them and then they all work. And then by passing messages back and forth to each other, they can all work in tandem. So that was a lot of stuff. So I'm going to go ahead and stop here and ask if there's any questions.
We're now going to talk about GPUs.
No, we're not going to touch GPUs. GPUs you can kind of think of GPUs as multi-core on steroids. Way, way, way bigger. Any other questions? Any questions online? So just to drive this point home a little bit more, in another graphic, this is another graphic that we have of the difference between distributed and parallel computing. In parallel computing, or you'll sometimes hear it called parallel computing instead of multi-core computing. This is one of these unfortunate things with computers where there's a million different terms that all mean the same thing. Multi-core computing is often called parallel computing. It's often called multi-thread computing. There's 5 or 6 other terms. Distributed computing sometimes is called networked computing. It's sometimes called scalable computing, many different things. So you can effectively think of it as being divided into just the basics is divided into multi-core, which is every processor has this big cloud of memory that it can access, and distributed computing where each processor has its own chunk of memory that nobody else can access, and if anybody else wants access to it, they have to ask for it. So another couple of terms that you're going to hear often in parallel computing. Now this affects MATLAB a little bit, and we'll talk about why in a little bit, is the difference between a thread and a process. A thread and a process are another one of those sets of terms that kind of apply to multi-core and distributed computing. A thread is a very lightweight stream of computations, so it's sort of like just the code that's running, and it assumes that it has access to another chunk of memory that a bunch of other threads have access to. And it can read and write to the same pool of memory. The reason I say it like that is because this is how MATLAB treats it. MATLAB will call a thread a very lightweight stream of computations that has access to a global chunk of. Yeah.
Is the thread like a P thread?
P thread?
A P thread? Like in C++, you have P threads.
Oh yes. Yeah.
Okay.
Yeah, it's
the same.
Yeah. P thread. Yeah, threads, P threads. Those are just the P thread is just the library and what lies underneath it.
Okay.
So yeah, a thread is basically just a lightweight stream of computations. It assumes that all the variables and all the data is stored in a big chunk of memory, and all it does is run computations. And when it needs access to something, it goes and checks that big chunk of memory. A process is effectively one of those cores, and is what I was talking about before, with a core and a chunk of memory stuck together. So it's a lot more memory intensive because it's a processing core and a chunk of memory stuck together. And you can think of it as it's an isolated channel in which computations can run. And it's also isolated from all the other processes. So those processes, so that means that it has its own little memory space with its own set of variables and data that it knows about. And it can't directly access any other processes set of data or variables. It might know, but it might have some sort of table in there where it knows where other data is, and it can go ask for it. But whereas a thread can just sort of go to the big library of data and variables and say, here, I need this, and pull it. A process has to go find out what other process has that data and go ask for it. And it might at first sound like processes are really inefficient, but they have a really big advantage that over threads, and that's that it doesn't matter, and that's that since those processes are all isolated, they can be anywhere. You can put them on. They don't have to be running on the same computer. They don't even have to be running in the same city. You can take them. You can stick them anywhere, and as long as that communication channel remains open, the program can continue to run. So in general, MATLAB in particular allows you to do both, but MATLAB, when they were implementing their parallel computing toolbox, they really focused in hard on the message passing and the processing and the process approach. They do also have a thread interface, which is faster, but they haven't. But even to this day, they'll say in their documentation that they haven't implemented all the functionality with threads that are available for processes. So in general, when you're doing parallel computing in MATLAB, you're gonna pick there's two different setups you can use: threads or processes. Generally, you're going to use processes unless you have a really good reason not to. Yeah.
Is it fair to say that the distinction is between the shared and distributed ends of this? Okay.
Yeah, exactly.
So, but then let's say if we're doing MATLAB, we would only do threads when we would do the shared computation, right?
Technically you can kind of do both. It gets a little bit more complicated in the sense of the way the way the actual software on the back end is implemented. Is that you can take those processes and group them all onto one computer, and it'll work, and it'll be a little bit slower than regular multi-core computing because it's still passing messages back and forth. But since those processes are so close together and they're all running on the same system, the actual communication overhead is really small. So
okay, you would still be simulating your distributed memory just on a shared memory space.
yes.
I guess my other question is that in the distributed memory, the parallelism isn't in the individual processes; it's between the passing.
Correct.
Okay.
It's in the passing. Yes.
I want to repeat the questions.
Thank you. All right. So the first question for those of you online was: is it correct to say that the main distinction in parallel computing is between shared memory and distributed memory? The answer is yes. And then the second question was: is it also fair to say that with processes, the main parallelization is in the communication between processes and not within the processes themselves? The answer is also yes. Kind of. Because you can get really fancy with processes. There's a version of this called hybrid parallel computing, which mixes the two paradigms, where each process also has a pool of threads it can use, but you don't want to do that if you don't have to. It can be really helpful, but MATLAB doesn't support that as far as I know, and you really don't want to do it if you don't have to. So, are there any questions I haven't answered so far? Any questions online so far? All right. In that case, let's talk a little bit about how to get started actually doing this in MATLAB. So, in MATLAB, when you go into the Research Computing Center, and I will actually switch off of here. When you go to the Research Computing Center, generally the interface you'll use is something called Open On Demand. And Open On Demand there's a login screen, and once you log in with your RCC credentials, you'll get a landing page that looks a lot like this. When you get here, you'll want to go to Interactive Apps and click on MATLAB. And this will give you a whole bunch of options. In general, the Slurm account you want to pick is GenAC Q. There's reasons for why this is, but that's a whole topic of its own workshop. Number of hours is how many. Generally pick as many as you need. Amount of memory, I would say always pick 64 if you can. Number of cores, 8, 16, doesn't really matter. Don't mess with the GPUs unless you really need them. And then MATLAB version, we have a bunch of different MATLAB versions installed. Right now, the latest we have is 2024B, but that's only because I've been slow and haven't installed 2025B yet, but I will. And then the extra module here is really only applies if you have some really special C++ external code that you need. In general, you don't use that. And then once you have everything set up, you'll scroll down to the bottom and hit launch. And eventually you'll get to a screen that looks, that's the right one, that looks like this. And this box will start out blue, and it'll say, and in the top right here, it'll say queued. And then eventually you can hit launch MATLAB, and you'll get to a screen, an actual MATLAB interface. So you can play around with those settings a little bit. I've seen scenarios where 64 gigabytes of RAM is not enough, and you can ask for a lot more. I think our current maximum on our free partitions is 512, or it's either 512 or 700 gigabytes. So the main reason you can run into out of memory errors on there is because one of the things I noticed about MATLAB is every single year, the memory footprint of MATLAB gets bigger and bigger and bigger because they keep adding more and more and more stuff. And so they use the Java virtual machine. They use Java in the background for a lot of their interface and a lot of their parallel computing, and that just requires more and more memory the more features they try to have. So, as I said before, MATLAB can do both shared memory and distributed memory computations. Which you end up using will really depend on a couple of things. The first one is it'll depend on how big of a factor in your program speed really is. And the second one is whether or not the second big factor is going to be whether or not the features and the functions in the libraries you want to use are built to support the thread interface, if speed is a really big deal. Because again, MATLAB hasn't quite implemented as many features for threads as it has for processes. It's really focused on hardware processes approach. So when you get into MATLAB, you'll see up on the home page, yes. on the Home tab here, there's a little parallel button here. This will help. This parallel button will give you the ability to choose which to set up your parallel computing. So what you'll do is you go to select parallel environment, and you'll see how you can pick either processes or threads.
Sorry, really basic question, but we first need the toolbox, right? The parallel computing toolbox. We need to have that installed.
Good point. And yes, I will get to that in just a second. So you'll pick either processes or threads, and then from there you will go. And one of the people in person made a very good point. In order for any of this to work, you need to have a package called the Parallel Computing Toolbox installed in MATLAB. Now, if you're using the Research Computing Center systems, we have this installed for you automatically, along with a whole bunch of other toolboxes. I don't know exactly how many we have, but it's a lot of them. So like we've got deep learning, parallel computing. GPU functionality was default from 2024 onwards, so we have that. And I know we've got bioinformatics, Simulink, and a whole host of others. So as long as you've got the parallel computing toolbox, you should have this option available to you, and you'll be able to pick either processes or threads. And they'll even say here in the parallel environment, not all parallel functions are supported with threads. So even MATLAB themselves recommends using processes, unless you have a good reason not to. Again, the reasons why you might choose threads. Again, the reasons why you might choose threads over processes, if the only reason you really would do that is if you're doing really memory intensive and processing intensive stuff where speed and memory optimization are really important. Most of the time, that's not the case. If it is, then you can always talk to us, and we'd be happy to help you figure that.
So what's missing with the processes is the memory managed, like you have to, okay.
Yeah, so that's a good question. The question was, what's the main thing that's missing from processes over threads? And that is the memory advantage. Part of the overhead that comes along with setting up processes is that somewhere's got to keep a registry of. There's also got to be a global registry of like what processes are what variables have access to what, and so there's a little bit of extra overhead, a little bit of extra memory overhead that goes into actually setting up the processes themselves. So it's not quite as memory optimal as threads are, because threads don't have to worry about any of that. But MATLAB has but processes were the original version of the parallel computing toolbox. And the reason for that actually has to do with how they built it in the first place. So MATLAB's a little interesting in that the way that they built their user interface using Java, but they also built the parallel computing toolbox using Java. So all of their parallel computing functions are built around the way that Java does parallel computing. And I know Java has multi-threading capability now, but I think if I'm not mistaken, it used to be focused around processes. And also they did that. They also did this because they eventually wanted to scale up to supporting full clusters. And of course they did also make that a separate product. So we don't have access to the MATLAB. I think it's called the MATLAB Grid Computing Engine, which is the distributed computing engine. We just have the parallel computing toolbox. So I think that as far as I understand, the grid engine sits on top of the processes interface. And because they have that extra stack, they focused really hard. Are there any questions so far? Online? All right, cool. So as I said, always when you're choosing your environment, MATLAB will default to selecting processes for you. Leave it at that unless you have a good reason not to. So once you get into actually writing the MATLAB code, there's a couple of things you'll need to set up within the code itself. The first thing is you'll need to create something called a parallel pool. And this is just a function within MATLAB that you'll want to put right up near the start of the script that you're writing. And if your code is multiple files, you'll want this to be up at the start of whatever the main file is. So you'll basically create a pool of parallel threads or processes using that parpool function and assign it to a variable called key. There's that parpool function takes two different parameters. The first one is a profile, and the second one is a number of workers. In general, you will always use the local profile, which means this current machine or whatever current machine you're on. And the number of workers that you'll select should never be greater than the number of cores you requested in this MATLAB setup screen. So if you selected 16 cores in the MATLAB setup screen, you'll want to make sure that the second parameter of that parpool function is not set any higher than 16. There's an interesting caveat with this too, that has to do with memory. And that is that one of the interesting side effects of using the Java virtual machine for parallel computing is that MATLAB will chunk up the memory and the total amount of memory it has available to it on its own, separate to how. So in general, if you're submitting a job to our job scheduler, you can specify in theory how much memory should go to each core. MATLAB will ignore that, and it will do it itself. There can be a very delicate balance to be struck between how many parallel workers in MATLAB you use and how much memory you select. So if you have a process that is parallelizable but very memory intensive per process, you might want to use less workers than the total number of cores you selected in the setup screen, because by selecting fewer processes, MATLAB will allocate more of the total memory to each individual process.
In that case, wouldn't you also want the cores to be the same because other ones are not being used?
Sorry?
So like if you say this is 4, right, but then on the open, whatever, it's 16, right? You selected 16 cores, you're not going to be using all of them then.
Actually, you're going to want to leave them as 16, and there's a complicated reason for that. And that actually has to do with our job scheduler, the way that SLARM works. So the question was, if you select 16 cores, but then MATLAB's not using all of them, wouldn't you just want to set the number of cores in your SLARM in your job setup to that same number? And the answer is, if you're doing this, so cutting down on the number of cores to increase the amount of memory each process has, you don't want to do that. The reason is because in the background, our job scheduler will convert everything to cores. I don't truly know why that is. That's a deep quirk of the job scheduler and how it was built.
Okay.
So in general, if you start running into out of memory error, in general, what you want to do is set up your parallel pool to be where the number of workers is equal to the number of cores you select, and only start reducing that total number of workers if you start noticing consistent out of memory errors. Because then by cutting down on the number of cores, each process gets more memory. So it gets a bigger slice of the total.
Just to be clear, the parallel advantage that you're getting is this number, right?
Yes.
It's this 4. So you, like, let's say if it was taking a certain amount of time, now it's divided by 4.
Yes. So the question was, so the total parallel advantage is proportional to the number of workers. The answer is yes. So essentially, the very basics of this is when you're setting up a script to run in parallel in MATLAB, one of the very first things you need to do in your script is set up the parallel pool, make sure it's using the local profile, and make sure that the total number of workers that you select, which is the second parameter, is equal to or less than the total number of cores you selected when setting up your job. Always make it equal to the number of workers. Always make the number of workers equal to the number of cores unless you start having memory. At the very end of your script, after all the computations and all the processing is done, you'll want to add another function called delete, and then put the variable you assign the parallel pool to into that function. And this is just cleanup. MATLAB probably will do this for you, but I've seen cases where that's not always the case. So it's good practice to always explicitly delete every parallel pool you create. So, any questions? Online? Now that we've gone through all of the boilerplate and all of the basic what even is parallel computing, now we can finally start talking about a couple of the main parallelization strategies that you're going to use in MATLAB. The first one is automatic parallelization. So if you remember looking back at the parallel environment, you'll notice that if you look at the description of processes, it says supports the full range of parallel enabled functions. Now, this is important because what that means is that MATLAB's already written a lot of its functions to automatically support parallel computing if a parallel pool is available to it. So, in general, all you'll have to do when using one of these functions is you'll have to tell the function somehow, hey, you can use parallel computing. And that will generally take one of two forms. Either the function will have a parameter in it that an optional parameter for the parallel pool itself, or it will have an optional parameter called parallel or use parallel, which accepts a true false value. Every function will do this a little differently. So you'll want to make sure and check and look at MATLAB's function documentation site within the MATLAB Help Center and look for automatic parallelism. And I should also mention right now that these slides are going to get sent to every participant. So even though I just clicked on a link in there, don't worry, you will get the slides with the link work. So using this documentation can help you find all the things that have automatic parallel support, and you can go and look at these and find what parameter you might need to use for parallel computing to enable parallel computing. A couple of them will even just do it automatically for you. There won't be a parameter. It'll just look and say, oh, there's a parallel pool available. I can use that, and you won't have to pass an argument at all. Some will have an argument you'll have to pass to it, and we will see that in the example coming up. Some will have, and some are going to have that parallel true-false that true-false argument for either parallel or use parallel. We'll see one of those too. Questions?
That's like an example of a simple function that they've already.
So a good example of that is the seek pdist function, which is pairwise distance of string data. So what this will do is take a cell array of strings or characters in this case, and it will compute the pairwise distance between all of them. I think it uses the Levenshtein distance, but I could be wrong about that.
Distance is that?
Huh?
What distance is that?
Levenshtein, I think.
What is the distance? Do you know?
I do not remember off the top of my head.
Okay.
I know the word, and I know that Levenshtein distance computes the minimum number of changes that you have to make to one string to get to another. And I forget exactly how it does.
Okay, that's cool.
So seek pdist is a good example of one of these kinds of functions. So in this one, you don't explicitly pass the parallel pool to it, but you have to give it this use parallel parameter, and you have to tell it true. This is specifically coming from the bioinformatics toolbox. Other functions are going to do this differently. Some of MATLAB's core functions are going to just say, hey, a lot of times what will happen is this first parameter is that if it sees that the first parameter that you pass to it is a parallel pool, then So with that said, one of the examples that we'll look at here is just generating a random sequence of a random set of 4 DNA sequences of 10 base pairs each, and then generating the pairwise distances between them and creating a little heat map of it. And I have this on MATLAB, and if you're interested, yes, we will send this entire code in the example is all the code you need to run this in MATLAB itself. So when you get the slides, you can just type this out word for word, and it will as long as you've got the bioinformatics toolbox and parallel computing toolbox, it should work. And I can get these tools to go away. Go back to here. So we'll go through this line by line, and I'll show you exactly what it does. So the first thing that we do here is we set up the parallel pool using four cores or 4 workers, and using the local parallel computing profile. Now I have my parallel environment set up to use processes, and so this will set up our parallel pool. Then we create just a little list of characters for the different DNA bases you can use. We create a 4x1 cell array, which is sort of like a Python list, in the sense that the reason we use cell arrays is because seq-pdist works on those, and cell arrays also can be of different length. Each one can be of different lengths. That's not important for this one, but it is useful. They can contain different data types too.
Okay.
So then we do a for loop from 1 to 4 to generate our 4 sequences. Within that, we start with a empty string, and then we randomly select 10 of these elements to get a string like ACTT, ACGBT. And then we stick each of those strings into the ith element of our cell array.
This automatically indexes the rows, right? And then just puts the 10 right in there.
Yes. Yeah, by doing this curly braces I, you're selecting cell 1 and all elements within that cell. And then this convert strings to characters is just chopping up that string into individual characters and saying, now there's 10 elements, stick it in this cell. Once we're done generating the sequences, then we call this function called seq-pdist. We pass it the cell array of our 4 DNA sequences. We give it the use parallel parameter, and we say true. And then we assign this to the variable d, which is going to be a distance matrix. And because of the way that MATLAB tends to store distance matrices, it tends to store them as single one-dimensional arrays. In order to generate a picture of this, a heat map, we have to use a function called square form to convert that one-dimensional array to a symmetric 2D matrix. And this heat map function will generate and display a heat map of those for us. And then lastly, we delete the parallel pool. Yes?
Why is it saying D is a 1/7 140 double?
Oh, this is a different example. So when I run this, this will be very different. That's actually the second example, because in the second example, we do this, but with a different strategy, and we do a lot more.
Okay.
So what I will do is go to the editor, then I'll hit the run command, and then you'll see in the bottom left hand of this corner, this busy, it'll say starting parallel pool on processes. It will take a little while for MATLAB to start up, because every time you start a parallel pool, the Java virtual machine has to spin up, and it has to spin up its n number of processes. Since I'm only using 4 processes, this is pretty quick, but be warned, if you ask for a lot of the more processes you ask for, the more time it will take to spin up these processes. And so at the end, we end up with this little heat map with the pairwise distances between those various DNA sequences. And again, I think it's Levenshtein distance, so it's not normalized.
Yes. You know what the actual function is, what it's doing? Like what task is actually parallel? What is the task that individual processes are doing to compute the distance?
That I don't know off the top of my head, and that would be a good place to go look at the bioinformatics toolbox documentation. A lot of times the documentation will either tell you outright exactly which parts are being done in parallel,
Okay.
or they'll tell you, or they'll maybe point you to the actual source code of the toolbox and say, hey, you can go look at the source code and go find, and then you'll want to go look for one of the other parallel computing strategies.
I think each process is picking a certain sequence and computing the distances with the other ones.
Yeah, my guess would be that if I had to guess, it would either be that they're doing that, or that they're
at the same
doing,
time.
yeah, or that each one gets a copy of one process,
Yeah, okay.
one, and then and then they do each, then do it again. Yeah. So, are there any questions online? All right. So I'll go back to the slideshow. So this is just one example of how you can do automatic parallelization within a single function. Again, if we go back to the MATLAB function documentation, there's a whole list of these. And there's a whole list of these. And actually let's see. Where is it? There it is. Actually look at this and see if it answers the question.
Yeah.
Input arguments. So yeah, as you can see, this has a whole bunch of documentation, a whole bunch of information that you can scroll through and look. Somewhere in here,
Right.
they're gonna tell you, yeah, right here, somewhere in here, they're gonna tell you pretty much what they do, and then computation. What they say here is that if true, then parallel computing toolbox is installed, then parallel computation occurs using par for loops, and that's good because that's our next example. That's what we're going to cover. If you don't have a function that is automatically parallel, you can actually do parallel computing yourself automatically using parallel loops. So in MATLAB, you've got your typical programming loops, you've got your for loops, you've got your while loops. MATLAB also provides a neat construct called par for, which is a parallel for loop.
This is more like pthreads now.
It's actually, so the question was, this is more like pthreads now, right? And the answer to that is, it's actually a lot closer to something called OpenMP. Have you ever used that?
Yeah, a little bit.
Yeah. If you've ever used OpenMP and you've used the directive either OMP parallel for, that's basically exactly what this is doing, except it's kind of condensing it. Yeah. So this is by far going to be one of the biggest workhorses for parallel computing that you'll use outside of the automatic parallelization. It works exactly like a for loop in that you say I want to go from I equals 1 to 10. That can be an index, and then everything within that for loop will be run in parallel. So what MATLAB will do is it will take those 10 iterations or those n iterations, and it will break them up and distribute them across the different processors. Now, how it does that is going to be done according to its MATLAB's internal job scheduling process, which I don't even understand. But what it will do is it will try to balance the work between the number of processes it has as equally as it possibly can. So in general, if you have 4 processes and 16 iterations, each process is going to get 4 of those iterations to do. Now, this does come with a very important caveat, and that caveat is that none of your iterations can depend on each other. If you've got anywhere in this code to run in parallel, if anywhere in that has a reference to I-1 or I+1, this will not work. And MATLAB's actually pretty nice about this because it will tell you before you try and run that. instead of something like OpenMP, which will probably just give you yes.
This example, when you say iterations going from 1 to 10, what you really want is 10 separate processes. But since you have 4 of cores, it has to divide that and in a sequential way.
Yes.
They get 4 and then get 4, and then you have 2 left over.
So the question was, so since we have in this example you have 10 iterations and 4 cores, and so if I'm understanding correctly, it's you're asking, will it break? Will it'll break that up? It'll look at that, give 4 to 1, or 3 to 1, 3 to 1, 3 to 1. Then there's 2, then there's 1 left over, or 2, 2, 2, and there's 2 left over.
Yeah.
So it will more or less do that, but it will try. But what it'll try to do is it'll take those 2 that are left over and then just assign them to a different core. So it won't be perfectly load balanced.
Yeah.
If I had made this example perfectly load balanced, there would be 16 iterations, or there'd be 5 cores, because then it could divide everything up to iterations at a time. But in general, it doesn't. You don't have to worry about the load balancing. You don't have to worry about perfectly load balancing it yourself. MATLAB will do the best it can for you.
Okay.
If you want to get into the weeds with that, you absolutely can. And then you can play around with how many iterations and then you can play around with the number of iterations versus the number of cores. You can do some really cool optimizations with that if you want to.
If you know the internal logic of how it's doing the scheduling, can you then reference earlier tasks?
You can get, I think you can. So the question is, if you know the internal logic of how the programs are working, can you then reference previous or other iterations? The answer is kind of. But you have to be really careful about how you do that. So I do not know exactly how MATLAB does this, but in something like pthreads or other programming constructs, there's something called a lock or a mutex. So those are constructs where you can basically say all the threads can run up until this point. At this point, there's a lock, and only one can pass at any given time. So by using that, once you get to that lock or mutex, you can only at that time can you reference different iterations, and you got to be really careful how you do that. One of the big pitfalls with that is it's very difficult to predict exactly when one process is going to do its work over another. So if you can get that low level, and you can get that low level control over how those processes interact, then yes, you can do that. But in general, you don't want to do that if you don't have to. So yeah, so in this case, let's go look at another example. And again, this example is exactly like the last one. It's basically just a really scaled up version of the previous one. Instead of generating 4 parallel sequences, instead of generating 4 delay sequences, we're going to generate 120 of them. And I'm just doing this to keep the examples pretty simple, so that I can showcase the main construct I want to showcase, which is parallel form. Now, one interesting thing you'll notice here is that there's two for loops here. There's a par for on the outer. There's nested for loops here. There's a for loop for I equals 1 to 20 and a for loop for I equals 1 to 10. The I equals 1 to 120 is generating 120 base pair sequences, just like the first example is. And then the 1 to 10 is generating, and then the 1 to and then the 1 to 10 is generating each individual sequence. So sticking 10 characters together, sticking them together, and sticking the ith cell. So this raises an important question, which is, can I parallelize both of these? And the answer is, again, unless you want to get really deep into the weeds, don't.
Right. Because on this one, each of the inner loop is working on a single.
Yes, exactly. Okay. Yeah, each individual one's working on a single processor. And unless you want to get really deep into the weeds and you want to try and mix the processes and threads, don't try to parallelize both.
What if I just put a par 4 in there? Like, what happens?
That's a good question. I'm I think you will either run into an error or you will run into some, or if you're lucky, you'll run into an error. If you're not lucky, you'll run into some undefined behavior. If you're extremely lucky and you should go play the lottery, then it will work perfectly. But that can get very tricky. In this specific circumstance, I think you could probably get away with it because this is
So
yeah, it's so parallelizable
Yeah.
that it doesn't. In this case, since the order of the base pairs doesn't really matter in this case because we're just generating them completely at random, then you could probably get away with it. But if you were working with real data, then the order of the sequences would very much matter, and you would not want to parallelize things. So, in general, you only want to parallelize one level of your for loops unless you have a real good reason to try and do more. So once we've generated everything, then we'll do the seek PDIST call again, and we'll get a much bigger and much more crowded heat map. So if I go back to MATLAB and I run the example 2 solution, which this is just, I don't know why I call them solution. This is just example. And if I click the editor and click run, it's the same setup as before. So it's a local profile with four parallel processes. And so this shouldn't take too long to start up. Assuming Java's feeling nice today. Yeah, so there we go. And then pretty quickly we get this very nice looking, but relatively useless heat. But this is really just to showcase that you can't, that if you want, you can actually control how you parallelize things. If you can't find a function that'll do the parallelization for you, you can do it yourself using these par4 constructs.
If I flip the loops and I make the other one parallel, would I expect the same advantage? You think?
No, I don't think so. And the reason is the reason is that each individual process. So in this case, if you were to flip the two loops and you would have 10, you would have 120 you'd have 120. I don't think you'd want to do that because each individual process would be doing significantly less work at any given time. Right. So just to make sure I repeat the question was, so if you were to flip this par4 loop and this for loop, such that the inner loop was the par4 and the outer loop was the for loop, would you expect this the same like symmetric advantage? And the answer is no, not in this case. If the amount of work was more or less equivalent, like for example, if you were doing matrix multiplication or something, then you could probably get away with this, as long as if you were looking at square matrices
Okay.
or something. Since the amount of work each process would do within this for loop is kind of tiny, you get a lot more advantage by parallelizing this outer for loop so that each process gets a bigger chunk of the work to do. And then you're not constantly starting and stopping processes.
But I was guessing because 4 is less than 10 and less than 120 that it would just get divided up. But it's because of the
it would get divided up. It would get divided up differently, but the scheduler would have to reschedule those every single. You're probably going to get better performance if you parallelize the
overhead between starting again and again. Different, yeah.
Again, you can get really fancy with this if you want to. But in general, if you're just starting out with parallel for loops in MATLAB, you're going to want to parallelize the outermost for loop and then leave everything within it non-parallelized. Again, unless you have really good reasons not to, or unless your data is so symmetric that the amount of work in the outer loop, the amount of work in the inner loop are roughly the same. Even then, I'd say parallelize the outer for loop and nothing else unless you have a really good reason.
The question about the memory aspect of this is so now each of the 4 processes have their own memory, right?
Yes.
So then when you initialize this thing, SI, the full, I guess I'm confused where each of the sequences live. Like what parts live? So the first 10, for example, or no,
So this is kind of why so this is a good question. So the question is, so since each of these processes get their own chunk of memory, how does this work?
yeah, exactly.
So this is actually why I initialized the cell array outside of the par4. So in this case, the cell array here lives in a global memory space.
Okay.
And then what's being sent to each process is actually an indexed work. So the processes only know of one index and their little chunk of data that they're
Right.
And that way, when they communicate that back to the master process, which is running everything else outside of the par4 loop, it will say, okay, here's the index I need to put this into, and here's the data. So go look at my global memory. Here's the ith index. Here's everything that needs to be stuck into it. Chunk it all together. So I remember that's a good question because I remember trying to do this the opposite way, and I remember getting errors. So yeah, it does get a little more complicated because there's also that master process that's running MATLAB itself. And that can store global variables like this. And sometimes in a lot of cases, you're going to want to do that.
So when each of the inner loop ends, it doesn't access the global memory yet. It does it at the end, the par4 loop. Sends all of it back at once.
Correct. You can effectively yes, I believe it does do that. You can think of each. This would get into the theory of futures and promises, and that's a little beyond the scope of this workshop. I'm happy to talk to you more about it if you want. But, yes, as far as I know, what this will do, this function call, it will send a little note back to the master process saying, hey, you're going to get this data back once everything's finished up. And then once this par4 loop is done, it should flush all of the threads back to the master process and populate the data.
Last question for the scheduling about the indexing.
Yes.
It does it before, like at compile time, it knows what the index is going to be. It's not doing it dynamically. It knows what indices will be sent to which process at what time. That is my question. It's like once it's done with these, then it'll go to these, then it'll go to these. Okay.
Yes. As far as I understand with MATLAB, so the question was, so does the scheduling of the individual processes happen at compile time or at runtime? And as far as I understand, the answer is technically at compile time, even though MATLAB is a dynamic is a interpreted language. As far as I understand, it does all that at compile time, and this is kind of why it has a par4 loop, but not a par while loop.
Okay, right.
Because par while loop means you don't know how many iterations you're going to need, but par4 means you do at compile time. So because of that, as far as I know, they've only ever implemented a par4 loop, and that's so you know how many iterations you're going to need to chunk up and schedule at compile. Are there any questions online? Yes.
So then is there no way to parallelize a while loop in MATLAB then? There is no power while loop.
As far as I know, and this is just based on my knowledge, which I will happily admit is incomplete. No. You cannot, and I don't even think you can do that within OpenMP or any other parallel computing construct, because a lot of parallel computing depends on that. It depends on that understanding that you know how many iterations you're going to have at compile time. You can get a little fancy with it if you want to use something like if you want to use something called MPI, but that's really deep into the parallel computing weeds. I think you could find a way to make that work, but within MATLAB's constructs, as far as I know, they don't support that by default. Any questions online? Just checking. All right, cool. So we've talked about this a little bit before, but one of the biggest issues you're going to run into with MATLAB with parallel for loops is loop dependencies. So something like this, where I'm updating an index of a big array, and it depends on the previous iteration. Now, because each of these iterations gets broken up and split onto different processes, and those run at different times and at different speeds and in different orders, you can never predict whether you're going to have access to that to any other iteration at the time you need it. So in general, MATLAB's going to tell you you can't do this. So now MATLAB is really nice in the sense that if you try to do this, it will tell you, and it'll say, no, I'm not going to do this. I'm not going to let you run this. And it'll underline the par 4 in red, and it'll give you a little indication saying the par 4 loop cannot run due to the way the variable a is used. And it'll give you a very nice explanation. I wish all error messages would tell you. If the par 4 loop is really complicated and the indexing is done somewhere deep in another function, you may get some weird, less helpful error message called unable to classify variable. But the effect's going to be basically the same. If MATLAB will run a checker before it runs any of your code, and if it detects that there's some loop dependency somewhere, or it detects that it can't figure out it can't figure out whether it's going to have a value available to it at the time it needs it or not. It'll throw an error and say, I can't do this. And either it'll give you this really nice explanation, or it'll say something like unable to classify variable. And that almost always, if you're doing this within the context of a par 4 loop, that almost always means that there's a loop dependency somewhere. It may not be in the main loop. If your par 4 loop is really big and really complicated and it calls a bunch of functions, it might be buried way down in one of those functions. But in general, it's gonna be this. So if you run into that kind of unable to classify variable error, or you run into one of these cannot run due to the way the variable a is used, in general, you're probably going to need to do some math to remove the loop dependencies.
You're free to do that inside, like in the inner loop.
That's a good question. So the question is, you're free to do this within the loop itself, right? That's a good question. And the answer is, I believe so. But for example, if I were to reference
This thing, yeah.
if I were to reference, let me see if it'll let me do that.
There should be a reference to the local process level memory for the individual process, right?
Yes. So for example, if this was j equals 2 to 10, and then I wanted to reference perseq of j minus 1. Why does it say that? Oh, because that's not valid MATLAB syntax. I'm thinking Python. There we go. So yes, you actually can do that, and the reason you can do this is because, as you said, this is a local variable. So any variables or arrays that you define within the context of that par 4 loop, you can actually do these references to different indexes. It's really only this I variable that you absolutely cannot reference other instances of it. So yes.
We have a question from online.
Yeah, question.
Can the data from a par 4 loop be used in other par 4 loops in the same code?
So, for example, let me just make sure I'm understanding that correctly. So if I were to, can this perseq variable then get used elsewhere?
I think that's what it means.
So no. This perseq variable is a local variable that's going to really only exist within the context of this par 4 loop. You can reuse the name in another par 4 loop, and MATLAB's a little strange in that it'll likely preserve the last value of that perseq, but in general, no, you don't want to use any variables that are local to within that par 4 context anywhere else. You can reuse the name, but you have to kind of think in your mind that this is a new variable. This is
like reusing the name is not a best practice either.
I mean, I'm saying you can do it, but you're really, again, Casey is correct. You really should not do that. So in general, if it's within the context of a par for loop, you cannot technically reuse it anywhere else. You can use the same name and it'll pretend to be a different variable, but for best practices sake, don't do that. Does that kind of answer the question? Any other questions so far? Okay, so I'll actually show you an example of. Good. Cool. I'll show you an example of that. So for example, if I was going to try and assign this to s of I minus 1, all of a sudden, so if I was going to all of a sudden try and say this is actually equal to s of I minus 1 plus that, now you'll see how this is going to give me an error. So I've tried to update the current variable of an index using the previous value of that index, and now the par for loop is saying, wait a minute, you can't do that. So
the first one that you tried, like with the access on I minus 1, that should also not really work, right? Because it's doing it all at once.
yeah, so in general, the variable that you're using in the par for loop, you can't reference any other values of that. So yes,
I have a question. So for D, remember D is like the sequence distance of all the different sequences, if I'm not mistaken.
this one?
Yeah, but you computed it
Yes.
using parallel. Oh, I see. Okay, thanks. Never mind. Sorry.
No worries. So because I've made the S variable to contain all the sequences at the global variable, the parallelization was just making individual instances of that,
right,
and then sticking them in their appropriate. Then the seq function takes that cell array and then splits it up again across a bunch of different columns to compute the pairwise distance, and then sticks it all back together in a global. So to recap, we've talked a little bit about the foundational concepts of parallel computing: threads, cores, processes, nodes. We've talked a little bit about the basics of parallel MATLAB, how to set up a parallel computing job in MATLAB, and how to set up orders. We talked about parallel functions in MATLAB and how to do automatic parallelization, and we talked a little bit about how to sort of do-it-yourself parallelization and using par. There are other constructs you can use. There's SPMD, there's a couple of others, but in general, these are going to be your workhorse. Automatic parallelization and par for loops are going to be your workhorse.
So it's single memory and
single
programming,
yes.
Different data.
Yeah, so the question was, is SPMD single program multiple data? And the answer is yes. So what that does is you have a block of code, and you've got the same function running on a bunch of different sets of data.
Yeah.
And then it'll just split that up it'll just split each function call up onto a different. So in general, it's very rare that you'll use that unless you're doing some really big statistics on different data sets. In general, you're going to use automatic parallelization and parallel for loops.
Is it the same as SIMD, IMD, single instruction?
Yeah. So the question is SPMD the same as SIMD? And the answer is effectively yes. Single program, multiple data, or single instruction. One's a little more granular than the other, but they're effective. Are there any questions online?
No.
In that case, any other global questions in general?
I guess I had a question about GPUs again. That really is where you see like the thread advantage, right? Because a GPU is going to be doing a bunch of threads at the same time.
Yeah. So the question is GPUs are really where you see the thread advantage, and the answer is yes, because GPUs are one global they're one global chunk of memory and this gigantic array of thousands of cores. And MATLAB actually has a separate construct you can use for GPU computing.
Mhm.
It doesn't work it's separate from the parallel computing toolbox, but it effectively works a bit like it's not quite CUDA. CUDA is not quite right. It's more like ArrayFire, which is really obscure.
Right.
I'm sorry, but it's basically what it does is if you're going to do GPU computing, instead of doing the parallel computing toolbox and actually dividing things up on threads,
Right.
you create an object called a GPU array, and that GPU array will sends the array to the GPU, and then it'll work. Then it'll do the computations on the GPU and send it back.
I guess my question is really more application oriented. Isn't that really where we actually see the advantage of parallelism?
GPUs?
Yeah, like like you were saying, let's say you have 16 cores, you're just dividing by 16. Wouldn't you really want, let's say, like millions of simulations at the same time?
So the question is, isn't GPUs where you really see the advantage? And the answer is, it depends. So GPUs are very good at a very specific kind of computation, and that's matrix. And that's usually 3x3 matrix computations. It's not everything. From what I've seen, and I will admit I don't know the full reasons behind this, not everything actually benefits that much from GPUs specifically over regular CPUs. CPUs are very, very good at fast, sort of generalized computations, and they're very, very good at fast, sort of general instruction sets. GPUs tend to have very specific things that they're very good at, and the overhead for learning how to use a GPU is actually a lot higher, even with MATLAB, than with parallel computing. So if you're going to do computation, GPUs are very, very, very good at matrix and vector math more than anything else. That's what they're really built to do. So if your computations are going to be doing big matrix or matrix vector calculations or tensor calculations, yeah, absolutely. Then you want to be using a GPU, and you probably don't even want to use MATLAB for that. You want to use CUDA or something like that. If you don't need if you're doing more like string-based tasks or more data pre-processing or some more complex tasks than just matrix computations in parallel, the speed up may not be as big as you might think.
Okay. I guess if I were to do something like this on a GPU, what would I say? I would say run like whatever number of processors I have, whatever number of cores I have on the GPU. Is that what I would say?
That's a good question. I actually don't know
Okay.
off the top of my head. I have to look that up.
Hmm.
The last time I tried to do that, I didn't actually have to specify the number of cores, because if I'm remembering how I did this correctly, I just tried to set up a simple GPU array, and the GPU computing toolbox in the background will go and detect what GPU card you have, and it'll pick up all the specs from that. Any other questions? Any other questions? All right. In that case, here's a whole bunch of links and references. And again, we will send the slides out to everybody who attended as soon as the recording for this video is done. And you'll be able to click on all these links. And again, and also, if for any reason you don't get them, feel free to send an email to support@rcc.fcu.edu and ask for them, and we'll be happy to get them to you. In that case, thank you all for attending.
Thank you.
And if you have any questions or need any help getting set up with this, just contact us at this email address, and we'll be happy to help you. We'll be happy to help you out. Thank you.